many acids? One, because there's only one hydrogen. Does that match this curve?
No.
So, H2A. Okay. What does that then become? HA officially minus. Then what does that become? Minus 2, because it lost a second H+. Okay. Once you have that general equation, now it's dropping that information into the curve. Where do you have each of these species? Okay. So we had H2A. We had HA. And I'm getting lazy. We had A minus 2. Okay. At the points where it all of a sudden became HA, what do we have? We have the equivalence point. What is true at the equivalent? Oh, crap, but that's close enough. What is true at the equivalence point? Okay. So that same process that we went through with this chart is what you would now apply to an amino acid. Okay. So what I want you to be able to do is fully interpret for anything I could potentially throw at you. Write down your equation and start processing out those individual spots. Okay. When it gets to an amino acid, and now we have to skip ahead again. When we get to an amino acid, now what I'm asking you to do is to draw the titration curve for an amino acid. So that's how this one becomes a little bit trickier. I'm giving you more information because I'm giving you pKa's, I'm giving you structures, I'm giving you what HA is. Now how would you draw the curve? Okay, well that comes from understanding what happened at each of those individual points. Okay. And our biggest one out of that, off of our titration curve, is when we know the pKa value. When do we know the pKa value? Where on this curve do I know pKa 1?
That's going to be carbs.
It's not where it starts. That's not the pKa. If we look up here, number 1, does that say pKa?
No, it's pH.
Does that say pKa? No. So right out of the bat, you should be saying it doesn't say pKa up there, dude. Okay. When can we find out information about the pKa?
Well, we already know what.
So we're told the pKa. Okay. So where on this chart, if I'm going to now draw a titration curve, would that pKa value show up? Where I can be like, that's where the pKa 1 shows up.
It's going to where it's going to go up in flat line. It's going to be in the.
And the flat line is our buffer range.
Right, and it's going to be in the middle of that, and that's your.
But that's the pKa. There's no pKa here.
But pKa is equal to pH.
When?
When it's
in that flat line area, in the buffer range. So what you can then go through and do is say, well, if I've got a pKa 1, okay, at, I can't even see that number.
2.2.
2.2, I should be a flat line.
Yep.
Okay, and there's that point. Okay, it's not a perfect flat line, so I'm being a bit exaggerated here, but it's pretty close. Where would I find pKa 2?
9.11.
At 9.11. So there's 9.11, and I would again expect a flat line. Where should I draw that flat line? Should I draw it here?
No.
Why not?
Down.
It needs to be further down because
you have to increase the amount of base.
we have to add base to get it to that pH. Exactly right. Okay. Do I have another pKa? At 10.07, using very rough approximate lines, I have another pKa that I could establish. How do I connect those values?
This whole line.
Okay. You'll notice after each of those flat lines, I have another rise. Why do I have another rise? The pH still has to increase. Okay? It will kind of rise and then ultimately flatline pretty much at 14. Why?
Saturated.
That is the saturation limit for water, which is our bulk solvent. Okay? Would I be able to say that that is pKa 3 if this is what my curve looked like?
You don't know.
No, that's the flat line of my curve. I've reached my saturation limit. Okay? I have to have that next rise. That next rise is because there's an acid species reacting with the base we're adding. Okay? At this point, I have no evidence of an acid species to react with the base because it's flatlined. Okay? So to know I have a pKa 3, I have to see another rise. Okay? With this information, I could then go through and deal with all my labels. We actually have, in this case, H what? Why 3? There's 3 pKa's. We're starting with H3A going to H2A going to HA going to A. Where do we start? All the way at the bottom, H3A. At the first equivalence point, which is where our pH spikes, at the inflection point, if you will, if you remember that, we become H2A. At the next spike, what do I have? HA. Okay. At the next spike, just A. I'm now in my completely basic state. I can't do any more big spikes. It's just going to flatline at a max pH. Okay. So it's that level of interpretation. From the full general titration curve, you are identifying where all those points were. I want to know all that information. Why do you know that that is the pKa1? Why is this pKa1? Why is it not here? Okay. Well, why is it pKa1? We're saying that the pH is equal to the pKa at that point. This equation is not valid. To make it valid, what do I need to add?
Your concentration of your products over your plus or log of products per reactor.
I think I got that one right. I'm not positive on that. So why at this point is the pKa equal to the pH? Nope, we said that's not valid. The conjugate base and your acid are in equal proportions, which means when I take an equal amount of A minus over an equal amount of HA, I get log of 1, which is 0. Only at that point does the pH equal to pKa. Okay. So really the best way to describe it is the pH never equals the pKa. But when A minus equals HA, now that term becomes 0, and when I solve, it looks like the pH equals the pKa. Kind of makes sense?
So at the buffer stage, the concentration of the H3A is equal to the concentration of H2A, and that is why pKa1 is equal to...
Perfect. Exactly right.
So
that would be all
okay.
the information you'd have to
That's what I
specify.
wanna know.
Yeah. And if you go back and look at that full-on labeled chart we did for the general acid titration, we did that. We went through and said, at the equivalence point, this was true. At the half equivalence point, this was true. Okay. And all of those true things ultimately get us to being able to identify the pKa of our acid. Okay. Questions on that? Okay.
You don't have to put like what the charge is at all these different spots.
Yes. So depending on the pH, you now are responsible for understanding what the charge is on that, in that sample. Okay. If we are at an incredibly low pH, the charge I'm going to be at is whatever the charge is on my structure. So if we, let's see, but there was a big old typo on this, dang it. So let's fix that typo real quickly. So this doesn't really even involve your titration curve to answer what the charge is. We would go through and look at our structure for tyrosine. We now have our fully protonated state. The very next step, pKa 2.2, is the pKa for our acid, right? It would get deprotonated. The very next pKa is pKa 9.1, which happens to be the pKa for the amine group. So what happens to it? It gets deprotonated. Okay. The very next pKa is the pKa for our R group. That gets deprotonated. Okay. So we would be looking at all of those structures and evaluating what's going on within them. So if we start at the extreme left, we have a charge of +1. And we move to, what was that, neutral? 0 to -1 to -2. Whoops, I'll fix that circle in a second. So far, so good? So yes?
Yeah.
Okay. So if I asked, what is a reasonable pH, or at what pH is the solution at a 0 charge?
Between 2.2 and 9.1.
Ah, but I asked for a pH. You gave me a range of pHs.
Oh, you're gonna find it there.
7.
Okay. Now it's going to come down to deciding. Okay. The only thing present can be this structure. So to have a 0 charge, I need to be at this structure and this structure alone. Okay. If I vary off of that pH a little bit lower, what happens?
You're gonna have positive.
I'm going to have some positive. Now the overall solution isn't just 0, it's a little bit positive. If I vary off of that pH by going a little too high, now it's -1. So at what pH is it just 0? Okay. It is the exact midpoint between those two. Okay, so if we look at our curve, so we'll have to remember this and go back to our curve. It would have been nice if I'd drawn it on here. So we had our go away. We're actually getting at that next slide. Just kind of a long way. So we had 2, we had 9, we had 10, roughly, right? So we have our 2, our 9, our 10. Close enough?
Yeah.
Okay. At position 2, here, what do I have?
H3.
Okay, that was our H3A, but remember we're now overlaying it over the top of our tyrosine. What was the charge for that first structure? Okay. Right? Yeah. So let me write that up top. That was our +1 species, followed by our 0, followed by our -1, followed by our -2, right? Exactly what we had off the previous slide. Okay. So at that initial point down here, what do I have? What is my charge? +1. Okay. At this point, what do I have? That's where I have, sorry,
0.
0. I wasn't processing it right in my head. Not your fault. At this next point, I have -1. At the next point, I have -2. So what I'm now asking is, what is the pH at that exact point? Because I asked for the 0 point. What is the pH at that point? Okay. If we have a perfectly drawn curve, we could probably estimate based off of what's going on here. I'm not asking you to estimate. I'm asking you to give me the exact point. Do we have some quantification that we could put in this to help us figure out what that exact point is? So I see Jimmy playing with a calculator. What are you looking at?
It's just the average of those two pKa's, so 9.
At this point, I'm at 9.11. At this point, I'm at 2.20. Yeah, 0. Okay. If this was a real titration curve, where is the blue point relative to those purple points? Exactly halfway between them. I know the pH at my purple point. I know the pH at the other purple point. 9.11, the other one is 2.20. What's going to be exactly halfway between them?
5.65.
Did you calculate it? Okay. It is 5.65. Well, what is exactly halfway in between? Where my structure equals 0. Okay. Scientists have gone through, or biochemists have used this information to predict something about separation or separatability. Oof, that was a bad word. Okay. If I adjust the pH to where most of my amino acids are neutral, would they separate in a system where I have a charged column? Okay. We look at separation, one of your, what is it, gel electrophoresis? We put an electric current through some gel and we watch how things move through it. They're moving based on their charge, their attraction for one side or the other of your gel. Okay. If they're neutral, should they move? No. So I can adjust the pH so that most of my amino acids are neutral or darn close to it. The ones that aren't neutral, they'll move. I can use this as a way to separate. So I could go through and determine where there's 0 every single time, or what I could do is tabulate a third value. That third or potentially fourth value is the pH at which your amino acid is 0, has no charge associated with it. Okay. That pH, okay, we end up referring to as the PI, the isoelectronic point. Okay. At that point, our amino acid is 0. Most of our amino acids, and I will move to the next slide in a second. That's a negative over there. Have an R group that is uncharged, which means when I look up the pKa values, I'll have the pKa value for my amine at 9 something, and I'll look at the pKa value for my acid, 2 something. I'll look at the pKa for the R group, there is none. I can't write 0, let's call it null. Okay, to determine the PI, what did we do? We took the average of the pKa's around my neutral point. How many pKa's are there for most amino acids? 2. What is the PI going to be? The same for roughly all of them, and in this case it's the average of 2 and 9. 6-ish, is that right? Okay. So if you look at the pK or PIs for most of your amino acids, you'll find that it falls in that range. Where we run into an issue is what happens with our amino acids that have a third pKa. We need to average the 2 pKa's around our neutral point. If we have a third pKa, should I average it in or not? Well, here, did I use the third pKa? No. So it should not get included in my average. Why not? Because if I average it in, where does my pH then fall? Somewhere further up here. Is that point where it's all neutral? No, we'd have some of whatever we said that one was, our H2A plus, H2A minus. Okay. So what we need to do is be very careful and methodical about which pKa's we average. Okay. And this gets nasty. Okay. I do not, for the life of me, understand what your textbook is referencing when they say what pKa's to average for amino acids that have an R group pKa. I do not understand it. Okay. I've looked and looked to find some easy way to do it, and I cannot find a way to do it. The only way I can see to do it is exactly how we just did it, which was what? We started with the fully protonated amino acid structure. We removed 1 hydrogen at a time to get my entire spectrum of charge. I added my pKa value information in. I found my 0 point, and I averaged the pKa's around that 0 point. That's how I get the pKa. Okay. That is stupidly longer than anything the textbook tells you. Okay. But again, I can't consistently follow the textbook's method. If I can't consistently follow it, I'm not going to tell you it because I can't do it. Okay. The only way I found to do it is to draw out the structures for it. Which means when it comes to the homework, you should draw out all of the structures. If you don't know the structure of the amino acid, well, crap, then you fail the exam. If I ask the question on the exam, what am I going to do? I'm going to give you the structure of the amino acid because I didn't tell you to memorize them all. Okay? So if I'm going to ask for a PI on the exam, I'm going to give you your starting structure. I'll say, this is the fully protonated structure. Do what you will. Okay? I could be trickier and say, this is some state of the protonated structure. Do with it what you will. Okay? Meaning I could give you for tyrosine, I'm probably going to regret having erased that. For tyrosine, I could have given you, stupid eraser. And asked, what is the PI for tyrosine, given that information? Notice, I've given you the pKa's that I want you to use, so you don't have to have them memorized, okay, for all three functional groups. Okay. And notice I've given you a structure. Does this structure exist? No. Why not?
Because it's neutral, or everything in there is neutral, which you would never have.
It would never ever be entirely neutral, because this is an acidic functional group, this is a basic functional group. What I drew it in the form of was the, I don't like charges, so I'm not going to show charges. Okay. You would then interpret this and say, okay, if I'm at a low pH, should that be protonated? Low pH is acidic. If I'm at acidic pH, should this be protonated? Should the acid be protonated? Yeah. If I'm at a low pH, what would happen to this one? It needs to be protonated. So you need to be aware of your protonated state and your deprotonated state. It needs to be protonated. What would happen to the tyrosine group? It would stay the same. It needs to be in its protonated state, which is exactly what it's shown in. Once you've got your initial starting point, now you can start playing with your pHs. Okay, what happens is you slowly make it more basic. Okay, kind of makes sense? As problems go, this becomes a very lengthy problem. I've seen other people go through and solve it very quickly, and as best I can figure out, based on what the textbook has given for PI calculations, somebody made up some numbers that worked for one or two of the amino acids, or most of them, and then they just memorized the rest. Okay? If you want to, by all means, you can go through and memorize the PIs. Okay? So it is the average of your two pKa's. If you have more than two pKa's, this becomes trickier. You're going to have to look at the individual charge states, and that depends on the reactivity of each of those amino acids. Are they acidic amino acids? Are they basic amino acids? Okay? So you have to have some structural information to do that interpretation. Questions about that? Okay. So again, if we looked at, let's see, do I have another sequence? Shoot, I don't. Okay, but I at least provided all the isoelectric points. So you can look up your isoelectric points. So this chart organized them alphabetically. Okay. You'll notice your pKa1, 2.34. Within a margin of error, your pKa1 is 2. Okay. It's the carboxyl end of your amino acid. pKa2, within a margin of error, about 9. I think 9.5 is a better estimate. Okay. But within a margin of error, you're looking at about 9. pKa3, all over the freaking map. And that's because they're all different amino acids, or different R groups. The PIs, look at the neutral PIs, the ones that don't have a pKa3. That first one is 6. The next one, 5.41. Margin of error, that's pretty close to 6. The next neutral one, 5.6, 5.9, roughly 6, 6, 6. Roughly 6, a little bit lower than 6, 6, 6, 6. All the neutral ones end up coming out to ballpark 6. Why? Because we're averaging the only two pKa's we have. the carboxyl, and the amine group. And there is some variation between those, but not a lot. When we go through and throw in our pK, our third pKa, now when we look at the pK or the pi, our average is now not an average of all three, but an average of two. But which two? So for the first one, it's the R group and our amine. For the next one down, at 2.7, it's the average of the R group and pKa1. Next one down, what did we average? R group, and pKa1. Okay. 3.2, R group, pKa1. 7.59, R group, pKa2. Okay. If you can find a standard pattern that makes sense or can explain to me how the textbook does it, by all means, go ahead and do it. Okay. The structural method is the only way that I've consistently gotten it to work. I think their method works for nearly all of them except for, I want to say histidine, but I could be wrong on that. I went through and calculated, and some of them it worked, their little explanation, some of them it didn't. Okay. The structural method will always work because that's where it's being derived from. Okay? Kind of makes sense? Okay. So this is their, this was our protonated versus deprotonated state, okay, which we've already talked about. If your pH is lower than your pKa, then what state are you in? Protonated, HA. If your pH is higher than your pKa, that means we're more basic than the pKa, we need to be in the deprotonated state, A minus. Exciting stuff, right? Questions? Okay, so some basics to remember before we move into chapter 4. We've got 20 amino or alpha amino acids. 19 of 20 are primary amino acids, which is in reference to how the structure is built. Your R group comes off of only the center carbon. Okay. Only 19 of 20 because one of them, proline, is secondary. If you look at the structure of proline, the R group comes off of that middle carbon and then does what? Rings back to the amine group. Is that going to change structural properties? Most amino acids, you can rotate this bond, that amine bond. Can you do that with proline? Nope, it's locked in because of the ring structure. Okay. That will change how the protein can fold and appreciate. 19 of 20, your alpha position is a stereocenter, and it is almost always L. Very rarely do we see D. It does pop up every so often. One exception is glycine, because what is the R group for glycine? Just an H. What's the other bond not shown? An H. So we don't have a stereocenter. We need 4 distinguishable groups to have a stereocenter. So glycine is our exception because we don't have a stereocenter. Okay. Isoleucine and threonine are a little bit trickier because they contain a second stereocenter. So if you look at them, you can track through them and you'll find a carbon atom that has 4 distinguishable groups on those 2 amino acids. Your uncommon amino acids, in some way, shape, or form, have been derived from the common ones. Okay. So for instance, as a quick example, because we've got serine up here, we could methylate serine. Meaning, instead of having a hydrogen there, we could put a methyl group, a CH3. Does that change its physical properties? Yeah. Now it's not very hydrogen bonding, which means it's now hydrophobic, and it would shift its category. Okay. Several of the amino acids have that type of functionality associated with them. Okay. And the last big one, which we keep referencing, here's a better average. So your pKa for the carboxyl is roughly, I would say, 2.2, okay, just to make it easier. And your alpha amino is 9.5. Okay. These are your basics that you need to have kind of memorized when it comes to the amino acids. Questions about that? Okay. We're starting to move now kind of into chapter 4. When we take our amino acids, we're going to combine them with each other. At one end, we have a negative end of our carboxyl, and we have a positive end of the amino. As we bring those near each other, they are attracted naturally because of those electrostatic attractions. What can end up happening is we can run a reaction, a polymerization reaction, okay? Or in the organic sense of the word, it is a nucleophilic attack of our nitrogen on the carbonyl carbon of our carboxylic acid. And this is such a lovely picture. You might guess why I don't like this. They're showing the nitrogen interacting with the oxygen. That's not really what's happening. The nitrogen is attacking the carbon. Okay? We kick out an oxygen which can pick up 2 hydrogens to release water. Okay? So it's looking at a mechanism of what's happening. Okay? Remember, biochemists seem to think organic chemistry does not exist. So what they do is they kind of fudge it and they say, well, we have no idea how it's actually happening, but these pieces are just doing it. And that's roughly what they're showing within this diagram. They're saying we're starting with 2 separate pieces. Those 2 separate pieces get close enough to each other. And I know that somehow in this reaction, an oxygen picks up hydrogens. And so I'm just going to circle the atoms that are involved in that, show that that piece disappears, and then just say, oh, wow, magically I have a bond. Jerks. Okay. But that is what they are doing with this diagram.
Seems like you would need one of the hydrogens to, or that nitrogen to be deprotonated first, which seems like it would be hard to do with like physiologic.
So those of you that have the organic understanding of what's going on, if we look at our physiological pH, we're looking at the carboxylate end, and we are looking at the nitrogen end. What I just described for the reaction was that the nitrogen must act as a nucleophile, and it must react with the carbonyl carbon. Right. To act as a nucleophile, what must it have? Not a proton. Nucleophiles are nucleus-loving, which means they love positive charge. Okay? If you love positive charge, that makes it negative. The nitrogen must supply electrons. Does it have electrons? By definition, no, it is positively charged. Okay? This is where the biochemists go, well, crap, I just know it happens. Okay? How do they know it happens? Well, they can test and they can see before and after that we start with structures like this and we end with somehow a structure with a new bond formed. The mechanism of how that occurs. If we try to do this in an organic lab, our experiment fails. We do not form the peptide bond. Why does it work in biology but not in a lab? There's an enzyme that brings these 2 near each other and says, okay, nitrogen, you have too many hydrogens. So I'm going to take one of those hydrogens temporarily away from you. Okay. By then accepting that hydrogen, now the nitrogen has lost an H+, it becomes close, neutral with a lone pair. Now the lone pair can potentially attack. We would form our tetrahedral intermediate, which we would remember from OChem. We say, okay, well now what happens? Well, we want to reform the pi bond, but that's a bad leaving group. O- would never leave on its own. So the enzyme that temporarily grabbed that hydrogen away from the nitrogen says, hey, oxygen, here you go, have another hydrogen. Okay? That'll help you act as a better leaving group. So it slides the hydrogen onto the oxygen, and then even further comes in and says, okay, oxygen, just come temporarily over here. I got a little bit of a positive charge. Just come over here. Just come with me. Saddles that oxygen away. We've now formed close to our peptide bond, except we still have an extra hydrogen on the nitrogen. Well, that oxygen is now really, really negative. So the enzyme says, hey, oxygen, look back at the structure where you just left. There's a positive hydrogen. Go get it. It runs off, grabs that hydrogen, spits out water. Now the enzyme releases everything and lets it all go. Okay? And everything is back to forming the bond. Each of those individual steps and how it does it comes from the enzyme doing it. Well, what is the enzyme? It's a protein. What makes the protein? Amino acids. What amino acids would facilitate, say, the removal of a hydrogen? Something that's negative. A basic element should be able to remove that hydrogen. What element might help pull that oxygen off? Something that's positive. So by understanding something about what our amino acids look like, we can then predict what amino acids should be in the reactive site to allow this reaction to occur. Okay? Really neat, kind of fascinating things. Okay? Questions about what's up there? Okay. So, the type of bond that we have here. What do we have? See if you can annoy me right out of the gate. What type of bond do we have forming?
I'm not going to call it a peptide bond.
Good answer. Peptide is a bad answer to call it. Okay. Generally accepted in most circles, but we're not in that circle now. We would call it an amide bond. Okay. Do we have any kind of interesting features within this bond? So here is where it's helpful to actually look at the structure of your amide bond. So there's an R group out there, an R group out there. And we officially have a hydrogen shown in there. What type of bond did I just make? Don't tell me peptide or amide. Keep it simple.
Polar bond.
Polar bond, go even simpler than that. How many lines are there?
Oh, single bond.
Single bond. What can a single bond do?
Rotate.
Rotate. Okay. That can rotate such that the R groups are now on the same side. Okay. So we can, with that rotation, we can generate different potential structures coming out of this. Okay. Would I predict the hydrogen to be acidic? Not really, because when we put a negative charge on our structure, which isn't particularly good for our nitrogen. Would I expect the nitrogen to be basic? Should it share those electrons with a hydrogen? Okay. Said another way, when we started, was the nitrogen basic? It was. That's why it picked up a hydrogen. Okay, to become NH3+. Now that we're at that neutral nitrogen, which we said could never exist on an amino acid, should it exist here? Should I protonate that spot? Okay. It could depend on the surrounding pH. It turns out we'd have to go stupidly acidic to protonate that nitrogen. So acidic that we're probably destroying something else. Why is that lone pair now all of a sudden not basic? Whereas if we'd drawn the amino acid to begin with, it was. 9 little words, or 9 little letters. Resonance. The nitrogen does resonance with the carbonyl structure. If I remove those electrons, I no longer have the opportunity for resonance, which then means not as stable. Okay? So because those electrons are involved in resonance, they are not particularly basic or reactive. What does that mean about the free rotation around the peptide bond? It's going to be harder because that nitrogen is sharing electrons. Okay? We can still do a rotation there, but it is now limited because the nitrogen wants to form that double bond. And as soon as we have that double bond, we can't do that rotation. Okay? Another thing to note that will keep coming up, oh, okay, that's not a big deal. It's just trying to reconnect. So while it's reconnecting, and I screwed it up when I drew this out. Note that when they drew it, they always started with the nitrogen on the left, the acid side on the right. Standard notation for all peptides. Maintain it. Oh, come on, you can reconnect. Okay, well, we're not going to have the last 15 minutes recorded. Maybe we can. We'll see. I'm just going to, I can't even advance, can I?